This simulation experiment was conducted on PC-Tran, a software that simulates in real time the operations of various nuclear reactors. This experiment analyzed the Westinghouse AP1000 reactor, which is a pressurized water reactor with improved use of passive nuclear safety. The various experiments simulated increasing and decreasing thermal power output through control rod leading, turbine leading, and reactor shutdown, otherwise known as SCRAM. These processes and the results of these experiments will be analyzed in the following video.
The first experiment involved increasing reactor power by inserting the rods from 2% insertion to 15% insertion, and then reversing this process. The reactor was allowed to stabilize at various increments, various temperatures, power levels, and the pressurizer data was recorded. This data shows how leading the reactor through altering the control rod insertion results in a relatively slow and steady change in reactor operations and a large reduction in the overall thermal power output. All reactor operations such as the turbine demand, pressurizer level percentage, and the temperatures change as a direct result of the changing reaction rate that results from the change of the rod insertion levels. Reactor power does not change linearly with control rod control, as the reaction rate does not have a direct linear relation to the control rod insertion percentage.
The second experiment involved leading the reactor through controlling turbine demand. Turbine demand was also decreased from 100% to 85%, similar to the rod leading experiment. Since this results in an instant change, the reactor responds less smoothly, even though this is a more realistic approach to how a reactor may have to operate. The power decrease was less dramatic than in the rod leading example. Turbine demand controls the actual output power of the reactor, instead of controlling the reaction rate directly. The data shown demonstrates the difference between the previous example of control rod leading and leading the reactor by essentially controlling the power output directly. Since sudden change puts stress on turbine components, using control rods to directly lead the reactivity rate would be better for the reactor. This results in faster change or faster wear rather than gradual changes. In actual world operations, reactors must keep up and reduce production with the power grid. This results in turbine demand being the driving factor and rod insertion having to match this. Excess heat can be vented, but excess electricity is difficult to safely dispense since storing it is difficult. Power plants generally plan by scheduling expected grid demands, but this is not always exact and results in some changes through turbine demand.
Experiment 3 simulated an emergency reactor shutdown,
known as SCRAM, or Safety Control Rod Activation Mechanism, or the reactor Tripp. This involves rapidly fully inserting the control rods or other control mechanisms so as to quickly reduce the reaction rate. Neutrons are absorbed by the control rods at a much greater rate than they are produced from fission, therefore giving a profound decrease in reactivity. As a result of this, all factors of power generation rapidly decrease over a short time period. The simulation shows power decreasing rapidly over several minutes, but this is obviously still not an instantaneous process. Decay heat will still be a substantial amount for several hours to days, but is easily managed by the spent fuel pool after around a week of active cooling.
In conclusion, the various simulations performed in these experiments show the difference between the various methods for controlling reactor operations. Leading the reactor through control rod insertion percentage results in a relatively gradual change in thermal power due to the nature of decay neutrons. Reactor control through turbine demand